back to this guy. And now let's do it explicitly. Let's replace the psi and the gamma with the cell periodic things. Right? So this part here is the psi k. And this part here is the gamma k. Right? And by the way, I've used the delta function to get rid of one of the integrals, let's say over k prime. And look at the table. When you go from discrete to the continuum, you get a 2 pi over a, so that canceled one of the a 2 pi squared. So I just have an a over 2 pi. Okay? Okay, so it's written in a very messy way, but it's an important equation. Let me write it in a clean way here. So the center of a Vannier function sitting on the home cell Okay? Any questions about the derivation, or it was a little bit convoluted? Sorry, and my handwriting, I know it doesn't help at all. So, okay, this is a funny thing. Maybe we should do a sanity check. This is obviously a real quantity, right? It's an expectation value of a normal operator. It's the center of an orbital. And you have an I here. So, you know, I think it's probably good to check that even though we do have an I there, that guy is real. So let's take the so to check that it's real, we take the complex conjugate, right? What else? So now I'm looking at the integrand. So I uk dk uk, I want to show that this is real, so that the integral is also real. So I get minus I dk uk, right? And so what can we do? We flipped the derivative from the ket to the bra, and to get back where we started, we have to somehow flip it back. So the trick is to remember that these functions are normalized over one cell, right? So the integral over one cell is 1. So we just differentiate this guy, right? So the derivative is now going to act on the two things on the left-hand side, but on the right-hand side, it's just the derivative of a constant, which is 0. And so that basically finishes the proof, right? I mean, that means that this guy is minus uk dk uk, and that minus sign cancels that minus sign, and we get back where we started, which is this. So, fine, this is real, and so we get the center of the Vannier function, okay? So now what I want to do is, in view of that equation, so for example, we have an A which has units of length, like this guy, and we have a 2 pi which has units of angle, right? So that sort of suggests that we introduce a new definition. And just by comparing one with the other, we get the famous equation. That's the Barre phase. So how long did it take us to get there? We've entered the Barre phase now. But I guess my whole point is that there's nothing mystical about the Barre. I mean, there is a lot of mystical things about the Barre phase, but it's also related to very intuitive concepts, like where the electrons are sitting. And for topological physics, it's actually exceedingly important, as we will see this afternoon. So even for doing numerics and calculating topological invariance, it really helps a lot to go back and forth, to think how to go back and forth between k-space and real space. It's really, you see the physics comes alive when you do that. So, if you remember very early on, the blue equation, that was our bulk polarization. P bulk equals that, and I can just now rewrite it using this expression for the Vanya center. Which is a very pretty equation, I think. So let's check that it makes sense. So polarization as units of charge, and then you have two-dimensional quantities here. One is the ratio of two lengths, and the other is the ratio of two phases. Okay? Okay, so now let's come back to your question earlier about when you change the phases, the choice of any functions is not unique. So let's see what happens there. And what that means is we're again back to that issue that we are always allowed to multiply eigenstates by phase factors. That we should not change the physics, right? So our eigenstates are the block states, so let's start with those. So I guess the technical name is gauge freedom, although this is not gauge in the electromagnetic sense, but it's in a different sense. But so let's say that I solved my diagonalization problem yesterday, and I got the wave function, and then I did it today on a different computer, and we're using different numerical routines, and it just came out with a different phase. Nothing wrong with that. And moreover, I'm doing that over a range of k points, and the phases are functions of k, these gauge phases. So let's see, let's check that this doesn't somehow mess up anything. Remember, however, that we are no longer totally free to play with these phases, because we set some rules when we got rid of terms in the integration by parts. I required that the gauge is periodic in this sense, right? So that means that to stay within the rules of the game, this transformation cannot mess up with that requirement, right? So what is the most general form of this phase factor, such that if the size lived in a periodic gauge, the psi tildes also live in a periodic gauge. So remember that what appears there, so what we want, since it relates what happens at k with what happens at k plus 2 pi over a, what we require is this. So our betas, as a functions of k, have to satisfy this requirement. So certainly, if beta is a periodic function of k, So if beta of k plus 2 pi over a is equal to beta of k, we're good, obviously, right? But actually, we can go one step further because beta only appears in the exponent, right? So we can use the most beautiful formula in mathematics, which means that we can actually put a 2 pi L here and exponentiate it. It doesn't spoil that relation. So in other words, the most general form for beta is a periodic function plus, I guess, this, right? So pictorically, so if you change the, if you plot this function beta throughout the Brillouin zone from 0 to 2 pi over a, so you can change the phases in some fashion like this. So at this k point you change it by this amount, at this k point you change it by that amount. And if you just have this part, then you change it by the same amount here and there. But more generally, you can have, so this would be, let's call it a trivial gauge transformation, where this point is equal to that, sorry, supposed to. But the rules of the game still allow us to have gauge transformations that do this, where you end up where you started. So let's call this beta of 0. So this is beta of 0, but this is beta of 0 plus 2 pi L. So let's call this a trivial gauge transformation, and this one a non-trivial. I think in view of what we've seen before, that sounds like a sensible description. And so the question is, what happens to this equation when we apply such a gauge transformation? Okay. Another definition, so let me just call this A of k. This is sometimes called the Barre connection. And so the Barre phase is the integral over the Barre connection. So let's see how the integrand changes before we see how the integral changes. So if the size change like this, the u's change in the same way. Check that. So how does the new, okay, let me write here because people in the back cannot see. So what does the new A, the transformed Barre connection, look like? So bar of k equals I u bar of k dk uk bar. So we have uk e to the plus I beta of k from the bra here. Now the derivative, importantly, acts both on the phase factor and on the function because the gauge transformation is k dependent. So you're going to get two terms out of that, okay? Let me go maybe a little bit quickly. I think it's fairly obvious. So when the derivative acts on the u, then the two exponentials just cancel and you get the same thing. So you have the a in terms of the untilted u's. So you get what you started with. But when the derivative acts on the function, it brings down a dp dk. with a minus I that cancels that plus I there. So you just get that, and then you get 1 from the normalization of the U. So the Barre connection is not gauge invariant, meaning just a fancy way of saying that it does change under this transformation. But the Barre connection in itself is not the end product. So what is related to the physical observable is the Barre phase, which is the integral of that, right? So obviously, if we now integrate this from 0 to 2 pi over a, and we integrate this 0 to 2 pi over a, and we integrate this from 0 to 2 pi over a, what we get is that the new phase is equal to the old phase plus what? It's the integral of a derivative, so it's the function, the difference between the endpoints, right? So what is that? Well, it's this. Beta of k plus 2 pi over a minus beta of k. I guess I'm setting k to equal to 0. So beta of 2 pi over a minus beta of 0 is 2 pi over L. So the Barre phase is also not gauge invariant. It's almost gauge invariant. It can only change by integer multiples of 2 pi. So is that okay? Well, let's go back to the physics. So the physical observable is this guy. That's where the phase appears. So if the phase changes by an integer multiple of 2 pi, how much does the bulk polarization change by? Integral of charge, right? And we've argued before that this quantity is only defined modulo E anyway. So that's consistent, right? But the Barre phase is nothing but the center of the Vanni function according to this equation. So we've just demonstrated that in this simple single band case, any gauge transformation that you can do only shifts the center, at most shifts the center of the Vanni function by a lattice constant. Having said that, that's not the only thing it does. It can also change the shape. So let's say the non-periodic part changes the center, but the periodic part, let's say this part here, can change the shape of the Vanni function, but in such a way that the center remains the same. So if we had some Vanni function here, and we've done a gauge transformation, after that, we may have ended up with something that has a different shape, but has the same center. But in addition to that, we may also have ended up, at maybe here, depending on the transformation. But this center is precisely the same as this one, okay? And that's the only thing that matters for the physical observable. Okay, so we have about 25 minutes. And I think what I would like to do is to talk about how we actually implement this numerically. So at some level, it's much easier to work with block functions than Vanni functions because those are the functions that we get out directly from our code, whether they are tight binding codes or ab initio codes, or even when you're doing analytical models like K.T models, you get somehow states in K-space. So how do we compute this guy? On the other hand, at least numerically, you work on a discrete mesh of k-points. So we want to have a discretized or finite difference version of this equation. And it's kind of interesting. So I thought I would go through it because even though it's a practical aspect, actually it also turns out to be kind of deep, let's say, because there is a right way of doing it, which is not trivial. So just to set the stage, let me discretize my Brillouin zone into 6 segments, so n equals 6. And let me define B as 2 pi over A, which is the length of the Brillouin zone divided by the number of segments. So that's the spacing delta K. So B and delta K are the same thing, but let me use both terms. So, if you had an ordinary operator, I don't know, the Hamiltonian or something, and you want to evaluate it, the average over the entire Brillouin zone, it's pretty straightforward. So you start with the continuum form. And then it just becomes, well, by that rule there, I guess, in the table, just becomes a weighted sum, a sum, all with the same weight of the contributions from each k-point. So, right? But we have something a bit special. I mean, our operator is a derivative, okay? So let's see how it works. So let's try the same thing, right? So that's our first guess. So like this, right? And now I do a finite difference representation of the derivative. So remember, B and delta K are the same thing. Right? So this is just a finite difference representation of dku. So this cancels that, and we get so here they are, the overlaps. Remember we discussed for a little bit whether these guys should be 0 or not. So they are not, and here they are, the overlaps of the U's, right? Okay, seems like a very reasonable expression. So by the way, why don't we have an 1 over n like we had there? That's because, this quantity is, let's say, order 1 in the discretization. But this quantity, if you take the spacing or b to 0, you get 1 minus 1. So the quantity in square brackets goes to 0. So it's actually, this minus that is order b. So think of a Taylor expansion. So right? So you have 1 from the normalization that cancels that 1. So the next order is linear in B. So this quantity is already order B. And so you sum, which is to say order 1 over n, right? So you sum over n points and you get something which is order 1. Here this was order 1, so you divide by n. So that part is okay, but it does have problems. Well, the first problem is that this object is not exactly real. That's not so good, because the Barre phase is supposed to be real, and we checked that in the continuum case it was exactly real. So, it would be nice to have a discretization that preserves all these properties. Of course, we can just take the real part, which is to say, since we have an I here, it's minus the imaginary part. And of course, the 1 goes away because it's real. So let's say this is attempt number 1. This is attempt number 2 that has solved one problem. Now we get something real. But it's not gauge invariant. Not exactly gauge invariant. So if you do a gauge transformation like the one we've been discussing before, I'll just go quickly, but basically, the phase that you multiply this guy by is different in general. It can be different from the phase here. So this guy, the whole quantity is going to change by some amount. So because of this extra phase factor, this is the transformed phase, is not the same as the original one. Okay? So can we fix that? We're almost there, so bear with me just for one more step. So the trick to make it gauge invariant is kind of cute. So the first thing I want to do is to restore the 1 inside the brackets here. So there was a 1 here that went away when we made it real because there wasn't, so it was like a minus I. But if I'm taking the imaginary part, nothing prevents me of putting an extra real quantity there. It's totally harmless.
So why do you want to make it gauge invariant now?
I mean, modulo, let's say 2 pi. Thank you, yes. So let's go back to this form. Sorry, I meant to put the square bracket here. So remember what I told you, that this object inside square brackets is order B, right? And B is small. If we have a fine enough mesh of k points. So I'm going to do, let's think of the Taylor expansion of the logarithm of 1 plus epsilon, where epsilon is a small number. So logarithm of 1 is 0, so and then you have at first order, we just get e, and then we have higher order terms, e squared. Okay, so what I want to do is to choose this to be my epsilon, my small parameter. Okay? So what I have here is precisely the quantity that I'm now calling epsilon. Right? So the logarithm of 1 plus epsilon, which is to say the logarithm of this overlap here, should be, to order b, is the same thing. So the difference is going to be higher order, like b squared. So is this clear? So let me maybe erase this. So I want to go from here to a new expression where I'm going to replace the quantity in square brackets by some other quantity that is the same up to linear order in B. And that's going to be that. And the argument is this Taylor expansion. Okay? So, my third attempt is this. Okay? So, this is it. This works. We're going to check. Maybe just a small thing. So, of course, the sum of logarithms is the logarithm of the product. So, this is the nicely discretized Barre phase expression. That is obviously real. And now let's check that it's gauge invariant in the same sense as the continuous one. So for that, we again imagine that we apply some phase changes to the states. How does this guy change? So what you can see is that when you change the phase, let's say, of this state by some factor, the gauge phase appears twice with opposite signs because you have the cat and the bra. So that cancels out, right? So in the end, we get back to the same thing. Ah, right. Okay. Very good. So, we have to be very careful with the last hop, let's say, the last overlap. That's the thing about these. The devil is in the details, but the details are pretty, so it's worth going through them because they actually contain a lot of physics. "10 minutes, okay, I think it's fine. So the procedure, if you want to implement this in your code, your tight binding code or whatever, so there are several steps. So the first one is you call your diagonalization routine and you get your eigenfunctions on a discretized mesh. And I guess, sorry that I erased it, I think. So my mesh had 6 points. So you do that from 0 to 5. Let me draw it again. So you do a diagonalization here, 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 and here. Okay, so you call your diagonalization routine 6 times. Okay? And then step B is that you let the last state, psi j equals 6, to be equal psi j equals 0. So that's our periodic gauge condition that we use when deriving all this stuff. So we cannot now change the rules. Okay? So what I mean by this is you don't call the diagonalization routine again here. You really just take whatever the computer gave you and you call that your wave function at the last point. So no extra phase factors. Now you run over all the points from 0 to 6, and you go from the size to the use. And the important thing, of course, is that by doing that, the U6 that you get here is different from the U0 that is there, but they are related in a precise way, right? So, of course, for k equals 0, this is just U. So, U of j equals 6 equals e to the minus I 2 pi over a x of u j equals 0. So you have to be very careful with this. And then the last step is just take the u's and compute the overlaps, product, and the imaginary part. So that's it. Oh, sorry. I want to show a figure. So this is again, you remember our parameter space alpha and beta. These are again 2 cycles. The blue one is the one that does not enclose the origin, so the Barre phase starts at some value, does something, and comes back to the same value. The other one is, the green line is the pump cycle, so the Barre phase changes by 2 pi. But now, of course, when you evaluate this expression, phases are only, there are branch cuts, so the phases, you have to choose what is the branch cut. So the typical choice that computer codes make is that the branch cut is there, so your phases are defined, from minus pi to pi, something like that. So when you're going through a cycle where physically things are smooth, at some point, like the pump changes overall by 2 pi. So at some point you're going to hit minus pi, and if you just take what the computer gives you, it will jump to plus pi. So you should remove that. So this is not a physical discontinuity. So, you remember we found physical discontinuities before due to edge states. That's not like that. So we don't have edge states. We remove the edges. This is a periodic system. This is a totally unphysical discontinuity, just because phases are defined model 2 pi. But if you're doing, changing smoothly the parameter of your system, you want to choose, you want to sort of compensate for that to get the green line. So just kind of the obvious thing. Okay. I think we're almost finished. Maybe I just want to make one final comment. I mean, there are many more things that one could talk about, but I didn't really go into the general theory of Barre phases, but the idea is that they are an intrinsic property, a geometric phase that is a collective property of all the wave functions taking along some loop in parameter space. Okay? And the Brillouin zone is periodic, so it's sort of like a circle. So that's why you can define Barre phases on it. So now we can go from a periodic Brillouin zone and wrap it around. So this is k equals 0, but it's also k equals 2 pi over a. And so forth. But in the paper of Barre, and in most topics of Barre's phases, you have some abstract parameter space, let's say lambda y and lambda x. And you compute the integral of the Barre connection around. So you have some state, u, which is a function of lambda, and you integrate the Barre connection u lambda I d lambda u from some initial point lambda equals, like that. And that Barre phase is really an intrinsic property of the wave functions on this path and nothing more. Okay? So this Barre phase that we're dealing with here in the theory of polarization is not quite like that. Because in this case, you could apply the same discretized formula. So you would diagonalize your Hamiltonian, and you would take overlaps from here to there, and so forth. But in the conventional Barre phase, for the last hop, there's no subtlety. Okay? So the last state is the initial state. So actually, the argument why the phases cancel also applies there, because yeah, it appears as a cat and a zebra, right? So clearly, that kind of Barre phase is really an intrinsic geometric phase, which is just a property of the wave functions. This one is not, okay? Because of this, which, okay, it's just a phase factor, but the point I want to emphasize is that it contains x. So this Barre phase that appears in the theory of polarization, which is also called the Barre-Zach phase or the Zach phase, contains, to use a fancy term, information about how the wave functions are embedded in space. Okay. Well, I've read that in a presentation by Haldane, so I feel like it's probably a proper term to use. But that's important, right? I mean, it's a fundamental difference. In fact, I also heard Haldane say this is not really a Barre phase. But well, yeah, you can call it a Zach phase. I think that's correct. So Zach wrote the first paper where this quantity was introduced. But so, and that's of course just coming back to come full circle. That makes a lot of sense because this has to do with the electrons moving in real space on a lattice, Wannier centers, all that. So, for example, if you shift the origin of your coordinate space, if you just shift your crystal, the Wannier centers change in the new reference frame. I mean, they have a different value. So the Barre phase should change in the same way, and you can check that it does, but in the discretized formula, it does just because of this guy here. So it's totally essential, actually. If you don't do this properly, you just get garbage in, garbage out. It's totally meaningless. So this last hop is key. It's completely key to describe, to then relate back to Vannier centers and so forth. Having said that, and I'll finish there, everything that I did was in one dimension. But if you go to higher dimensions, there is a lot of interesting new Barre phase physics. Like in 2 dimensions, your Brillouin zone has 2 parameters, and you can define the conventional Barre phases where the last state is really the same as the first one, so you don't go across the Brillouin zone. And these also have interesting meanings, so they are related. For example, if this is a Fermi surface or a Fermi line of a 2-dimensional system, then this is related to the anomalous cell conductivity and all that. So the conventional Barre phases also appear in K-space. But these ones that go from one side of the Brillouin zone to the other are a bit special. Okay, so we're supposed to finish in 2 minutes. And yeah, I think, I did want to talk about Chern numbers, but clearly there is no time for that. It's a bit of a pity. Maybe I can give you my notes, but maybe I'll just ask. I should stop here, right? So, any questions or comments? Yeah. Oh, yes. That was a topic of my PhD thesis. That was a topic of my PhD thesis, actually. No, but please go ahead. So I like that, yeah.
No, I guess what construction you're running there, there's some kind of tensor structure that allows us to measure distance between states.
Absolutely. So the quantum, right. So you can define a distance between quantum states. And yeah, this is actually interesting because it actually relates back to Vannier function. Let's say you have 2-wave functions. I guess one way of doing it is 1 minus right, so this is one way of defining the distance, I guess. So if the states are the same up to a phase, the distance is 0. If they are not the same, the distance can go up to 1. Now, in this context, let's say you have some parameter, and then what is interesting is to Taylor expand this, and what you get, so that defines a metric. That's the quantum metric. Which is, so if our space is K space, then this metric is a function of K. Yeah, but since I didn't introduce the Barre curvature, unfortunately, anyway, so there is this geometric tensor that the real part is the metric and the imaginary part is the Barre curvature. I just say one thing. The integral of the metric over the Brillouin zone gives you the quadratic spread of the Vannier function, the one-dimensional Vannier function. So that's kind of pretty. So the Barre phase gives you the first moment. So it's the center of a Vannier function. And the quantum metric gives you the variance or the spread, the spread of the in K-space, okay? So since the center is the polarization, you can somehow intuitively think that the quantum metric gives the quantum fluctuations in the polarization. So the polarization is a ground state quantity. It has to do where the center of mass of the electrons is, and if it's displaced with respect to the ions, you get a polarization. But there is also it has quantum fluctuations. And somehow, this has units of length squared. So you can define a length by taking the square root of that. And that actually, this length is a measure of how localized your electrons are in your insulator. Okay? So it sort of puts on a very rigorous footing the intuitive notion that in an insulator, electrons are localized, even though the charge distribution may be all spread out. But in some deep sense, if you apply an electric field, you don't get a current. I mean, a DC field, you just get a displacement, you induce a polarization. So they are bound in some sense. And this quantity quantifies very rigorously the notion of localization of electrons in insulators. And across a metal insulator transition, this diverges and all that. So, yeah, so the geometric structure that you were mentioning, one can work it out for this particular problem, and all these different concepts, phase, curvature, metric, do have meanings, outstanding meanings in the context of Bloch electrons. I don't know if that was sort of, maybe it was too much of a digression, but okay.